Okay, so it would be like this. First, we'll have to do uh, Q is equal to mass into latent heat of vaporization. Mass is 10 grams into 2300. So this gives me how much? 23,000, or yes, 23,000 joules.
Mm.
Q1. And then I will need energy to drop the temperature by 50 degrees, because currently it's 100 degrees centigrade. I want to drop down to 50. So what I'll do next is Q2 is equal to mass is 10 grams. Specific heat is 4.2,
Mm.
and change in temperature is 50. So 10 into 4.2 into 50 gives me 2100.
Okay.
10 grams, 4.2 mc delta theta. Okay. And the final should be the sum of these two. So total heat is equal to uh, Q1 plus Q2, which is equal to 23,000 plus 2100. Okay, so this will be 25,100.
Mm.
So you just have to see in these type of questions, the important thing to know is first to realize, is it just one process, or are there two processes happening? Is it just the change of temperature, or is the state of matter also changing in these questions?
Okay.
Okay, so if it is just change of state of matter, then we'll use this one, as we discussed before, for change of state of matter.
Mm.
Okay, if it is just temperature raise, then we will use this one, Q is equal to mc delta theta, for change of temperature. And if it is both, then we'll use both. I mean, we'll calculate both. First, the energy required to change state of matter, and then the energy required to change temperature, and we'll add the two energies, and we'll get the final answer.
Okay.
Units should always be mentioned, so joules. Got it?
Oh, I just need to write it down.
Mhm.
Okay.
Uh,
Mm.
by the way, we did fourth in the class, right?
Yeah.
Fourth and three, these three, four were done. All right. Six, please. What's the answer?
161 gram.
161. It's close. But so what's it asks you to calculate 3 kilowatts electric kettle, 2 minutes. boiled off power, energy, and then energy you use and mass. So power over here, the way you do it is power is energy by time.
Mm.
So power is equal to q by t, and rearranging this you get q is equal to power into time. So q is equal to power is 3000 and time is 2 minutes. So that would be how much? 2 minutes would be 120 seconds.
Mm.
So 3000 into 120 you get 360,000, and then you use q is equal to mass time latent heat of vaporization, and q by lv is equal to mass. um, Mass is equal to 360,000 divided by latent heat of vaporization is 2300, divided by 2300 you get roughly 157 grams.
Mm.
156.52 grams.
I did 360,000 divided by 2,230.
Does it give it as 2230 over here? Oh, that would have been, it's 2300. That's why you got a slightly different answer.
So would my answer be correct though?
Uh let's see. This is an error in copy pasting a value, so I think just 1 mark would be deducted for this one. If it's
Mm.
like a 4 mark question, you'll get 3 marks on this.
Okay.
All right. So
Yeah.
in Cambridge, what happens is that for any error that you commit, for example, in the initial steps, if you make an error in copying some value, and as a result of that, the error it gets carried forward. So your marks will be deducted only in that particular step, and for the remaining steps, if you have done those right, you'll get the marks.
Okay. Ice is good, I guess, because they produce low amount of heat and they
Ice.
absorb
Hmm, hmm.
heat.
Ice has a very high specific latent heat of fusion. So the
Mm.
amount of energy that you need to give to ice so that it converts into water is very high. It doesn't melt easily. So
Mm.
in that same staying as ice, it keeps on giving the cold vibes, let's say, for a longer length of time. That's why it's good. The reason is that ice has a very high specific latent heat of fusion.
Okay.
Okay, and why do you use superheated steam
I
to
don't know what
trans?
that meant.
Hmm. This one is that again, water has a very high specific latent heat of vaporization.
Mm.
Superheated heat. So, for example, it would stay as in its current form and wouldn't change form as easily. It would give off a lot of energy before changing form, before changing back to water. So if you
Okay.
want to give heat, you use steam, because steam it would give off a lot of heat before it gets converted into water. Similarly, high latent heat of fusion for ice, it means that it would absorb a lot of heat from the substance before it gets melted. For
Right.
both 7a and b, the amount of heat required to change the state of matter is very high. So they would be absorbing and giving off heat. In case of heat transfer, they'd give off the steam would give off a lot of heat before it gets converted into water and cools down. And the ice, it would absorb a lot of heat from the drink and make it chill faster before it changes its state and converts into water.
Okay.
Okay, water is stored in a bag of porous material to a draught of air. Hmm. 8.
Mm,
Okay, so some water is stored in a bag of porous material such as canvas, which is hung. Draught temperature of water is lower than that of the air.
because the bag is made of like a fabric that allows the water vapor,
Hmm.
but not
Ag-
liquid water
ag-
to pass
hmm.
through.
Again, the answer lies in the specific heat capacity. The specific heat capacity of water as compared to other materials is high. So, for example, if you look over here, uh, for aluminium, I have to give just zero point 0.9 joules of energy to raise temperature by 1 degree centigrade. For water, I have to give at least 4 times that energy. Okay. So the
Mm,
temperature of water does not rise as easily as other materials, and this specific property of water makes it a good coolant. That it absorbs a lot of heat from whichever substance it is supposed to cool, and its own temperature does not rise as much. So it keeps on absorbing that heat from that other material. Because if its temperature also rose and became equal to that other material, it wouldn't absorb any more heat, right?
yeah.
So the same with over here as compared to air, the gases in the air, the specific heat capacity of water is higher, so it absorbs a lot of heat and its temperature does not change as much, whereas the temperature of air would have been higher when exposed to the same amount of heat.
Okay. So again, like this is also like about the
The
specific
same
heat.
thing, specific heat capacity, yes. For 8 and 9, that is the reason specific heat capacity. So for 9 as well, if you have got heat energy, that would make milk go bad. Okay.
Mm,
But if it's put in water, the water it would keep on absorbing energy from that bottle of milk and would let milk stay good for a longer period of time, because water it absorbs that energy and then when it evaporates it takes away that energy. So that the same reason water is used as a coolant. So
okay.
specific heat capacity is the more precise answer for question number 8 and 9. For the 10th one, what did you get as your answer?
Mm, wait. I know I did something wrong. 1 second.
What did you get as your initial answer? What answer do you have right now? Maybe it's correct.
Did you say something?
I said that what's your what answer did you get for question 10? Maybe it is correct. I mean, it's just you thinking that it's wrong. What if it's
Mm,
correct?
because I did something else. I can't find the. I got 100.9.
1200 would be the answer, and here's how. So you have got C, specific heat capacity, as 4. So first of all, let's see what the question asks for. The question asks for what, how much heat is required. So it's asking for what's the value of Q. Hmm. Okay. So Q is equal to what? Then the values that it gave me as the data is mass is 10 grams.
Hmm.
It gives me C as 4 joules per gram per degree centigrade. Okay. And it gives me change in temperature. So temperature changes from 50 to 20. So it means there's a change of 30 degrees centigrade. So just looking at the data, I know I can easily use the formula Q is equal to mc delta theta and get
Hmm.
the answer. So 10 times 4 times 30.
Okay.
Okay, so there's this one easier trick that I'll give you for physics, would work for chemistry as well, and maybe for math as well. But there is this one very simple, method of how to solve this question. In each question, first of all, find the requirement. What do you have to
Hmm.
calculate? So, what's the requirement in the question? That's the first step. The second step is to, lay before you the data given. Okay, so you analyze the data given, what
Hmm.
data is given, and the third step is that you find connection between data given and requirement,
Okay.
and that will be your solution. Always, all of these numerical questions in chemistry, in physics, would work even in math. The first and foremost requirement whenever you get a question is you see what is it asking me to calculate, or what does it ask me as an answer, what value do I have to give as an answer, what's usually the
Hmm.
unit of that. So I look at the requirement, then I see all the information that's given in the question. Okay, so maybe even write it down like I did over here. So then the next thing is that you find the connection between the values which are given and the value which is required to be calculated. Sometimes it would be done in just one step, like over here, and sometimes it would be done in 2 or 3 steps. So you have to make that complete connection. Okay, this information is given, it would lead me to this, which would lead me to this, which would lead me to answer. In most of
Hmm.
your questions, it would be just one step. In some of them, it would be two or three steps. It would never be more than three steps in your IGCSE level.
Okay.
All right. Okay. So having done this, there is just one more thing with regards to this topic of heat that we have to discuss, and that is the modes of transfer of heat. So heat, we know, we have looked at these before in other classes. Okay, so there are three methods of transfer of heat. Do you know
Hmm.
what those are?
Three methods of transfer of heat.
Hmm.
Wait, isn't it?
Hmm.
Wait, I know these.
Hmm.
I think I learned them.
Okay,
So we have conduction, convection, and radiation.
excellent, excellent. So we have got conduction, convection, and radiation. Okay, so let's look at these three together in a holistic manner, and then we'll see if there is any further details that need to be taken down from the chapter or from the book. Okay, so conduction and convection, they require a medium for heat to pass through.
Hmm.
So they require medium. This also requires medium, and this one does not require a medium to pass through. I'll elaborate this further. What does it mean, does not require medium to pass through?
Like it can. There's radiation in outer space as well, basically.
Excellent, excellent, excellent. So in space where there is no matter and there is actually space, there aren't any molecules, or there isn't any matter, radiation would help us carry the energy even through space as well.
Oh, one second. I need to get water.
Sure, sure.
Okay.
Hmm. Okay. So we have got these three methods of transfer of heat, and the first one we said conduction. Then there is convection. These two require a medium for transfer of heat, and radiation. It does not require any medium for transfer of heat. So how does conduction? It transfers heat. So conduction it transfers heat simply by the use of principle that heat it flows from a region of high concentration to a region of low concentration. So for example, if I've got one molecule in a substance and I give it energy, its energy would
Mm.
be greater than that of neighboring molecules. So to get an equilibrium along with the rest of the molecules, it would pass some of its energy to neighboring molecules. Now, these two molecules, they have got energy slightly higher than their neighboring molecules, so they'll pass on some of their energy, and this way, the whole material it gets heated up. Conduction is most commonly observed in case of metals. So, for example, all the cooking utensils that we have, they are made of good conductors or metals. Cooking utensils, they aren't made of plastic because plastic is a bad conductor of heat. Wood is a bad conductor of heat. And this bad conduction of heat, it also comes into play. So all the utensils that we have got, they are made of some metal, and the handles and holders of all these pans, they are made of an insulator. So their holders
Mm.
are usually made of either plastic or wood. Otherwise, you'll have to use mittens to hold this. So, for example, the tawa or the thing on which we cook roti,
Yeah.
it's completely made of metal, and
Yeah.
its holder it has got a wooden or plastic holder. Its holder isn't metallic for the reason that it would get heated and we wouldn't be able to hold on to it. The same way we have got kadahi. So kadahi, its ears are also made of the same metal. So most of the times we'll have to use either a cloth or a mitten to hold that kadahi for the frying, the thing in which we fry pakoda or samosa. Okay, so that's this conduction. If we are to write down the definition of conduction as well, let's do that too. uh, Conduction is the flow of thermal energy through matter from places of higher temperature to places of lower temperature without movement of the matter as a whole. And we know that since conduction it involves transfer of energy at molecular level from a molecule to its neighboring molecules, automatically the substances which have got their molecules closely packed together make them good conductors.
Okay.
And that is the reason that metals they are good conductors of heat. The other method that we have got is convection. Let's first write down the definition of convection and then we will discuss it a bit. Okay. Um, Conduction, have you noted it down?
Yeah.
Let me know when you've done written this as well.
Okay. I wrote it down.
Okay, so hmm, hmm. To understand convection, if we have got, first of all, as we said for conduction, it's the mode of transfer of heat mainly in metals. Conduction, it works for fluids, which means both liquids and gases. So the way it works is, for example, we are heating this particular beaker over here with water in it. If we heat it over here, the molecules at this particular place, as their energy raises, they'd vibrate more. The distance between these molecules would increase. Are you following me?
Yeah.
Okay, so when the distance between these molecules it increases, their density, would it increase or decrease?
Can you repeat?
If I heat this beaker and the
Yeah.
molecules they vibrate, in solids they can't go, they are packed together, so they can't move farther apart. In
Yeah.
liquids there is more room, so the distance between the molecules it increases even further. When the distance between the molecule it increases even further, the question is, would the density of the water or the liquid over here, would it increase or decrease?
Increase.
It would decrease. Why? Because the volume has increased. For same mass, volume has increased and density is mass per unit volume. When the denominator volume increases, the overall density it goes down. So did you get this thing? Why the density would decrease?
Yeah.
So same mass spread over a larger volume. Their density has decreased, but the density of water up over here, that is more. So this dense water or denser liquid, it would come down and it would replace this less dense liquid, which would go up. And as it goes up, it carries the heat energy with it.
Okay.
Okay, so same thing keeps on happening. It goes up there, maybe it loses some of its energy to the neighboring molecules over there. Its density again, it comes down. By that time, the density of the liquid down here, it has increased, so this one goes up. So it keeps on happening in the form of current.
Hmm.
Okay, that is where we get the name of convection currents from. These convection currents, they are observable in wind which blows over the land. So from sea, hot air, it comes to the land, and then as it loses its energy, it goes back to sea, and we have got those current cycles. The same phenomena, the same way it happens with air as well. And by the way, this is the very phenomena which helps hot air balloons go up. So you must have seen the air lanterns. What we do is we simply light a candle under that lantern. It makes the air just above the candle become hot. It becomes hotter. It loses its density. It goes up, and the denser air, the cooler air, it goes down. So the hot air going up lifts up the lantern. The hot air going up, it lifts up the hot air balloon. All right.
Okay.
Okay, we'll note down the definition for the third one as well, which is radiation. Radiation is the method which allows heat to transfer without a medium. So if there is no medium, then how does heat it gets transferred? It transfers by means of electromagnetic radiations.
Hmm.
So radiation is the method of transfer of heat by means of electromagnetic radiations. Let me write that down as well. Okay, then maybe the last thing that we have to know is that which substances they are good emitters and absorbers of heat, and which surfaces they are good or bad absorbers of heat as well as emitters of heat. Um, Dull black surfaces are good at both emission and absorption of heat, whereas smooth, shiny surfaces are bad emitters as well as absorbers of heat. This is one reason that people in very who live in regions of hot climate where there is a lot of sunshine, they usually wear white and yes, shiny colored clothes. Not exactly shiny, but white colored clothes. That is also partly the reason that uniforms for school they usually have white shirts, especially for summers.
Hmm.
And the sweaters that we have usually are of darker colored because in winters it help absorb heat energy and help the person keep warm.
Hmm.
All right. Um, have you noted this down?
Yeah.
These 2 points. Okay. The last is the construction of a volume flask. So, sorry, vacuum flask. I said volume flask. The vacuum flask it makes use of all the things that we have discussed over here. So over here, the stopper is that of rubber, not a good conductor, so heat cannot escape from here. Then these silver surfaces they allow the heat to not get out of the flask heat by means of radiation because silver and shiny surfaces they would reflect back heat, and in between over here we have got a vacuum so heat cannot pass out of this flask by means of conduction and convection.
Okay.
Okay, so sometimes there are a few MCQs or maybe a 2 to 3 marker question in your exam related to the construction of the vacuum flask. It uses all these three. I mean, it prevents the escape of heat from within this whatever is contained within this vacuum flask. So if you keep something cold, it cannot get absorb energy from the surroundings. If you keep something hot, it cannot lose its energy from within the flask to the outside. Okay.
Okay.
Okay. I think that's it for this chapter. This topic of heat is complete. In the next class, inshallah, we'll start with the discussion over waves. All right.
Hmm.
All right. See you in the
Yeah.
next class then.